Thank you all for coming back and joining us. Sorry for the delay there, but another exciting afternoon and a continuation of the reactive transport modeling. This will be our second tutorial session, and Roelof, Versteeg, and Becca Rubenstein will lead us off here. So go on, proceed.
Okay, thank you. And so my name is Roelof Versteeg, and I'll start this presentation and then hand it over to Rebecca about halfway there. So what the objective of this session is first to talk a little bit, and we'll echo some of the material and think even some of the same figures as the presenters in the morning there. So we'll talk about the challenge of a possible approach to scaling of reactive transport modeling of microbial processes. We'll introduce a hands-on online modeling tutorial with interactive reactive transport modeling, and we discuss and present the pipeline for automated microbial modeling using KBase and pFlowtrain. So, well, you know, why use reactive transport models? Basically, Tim already answered this morning, but basically microbes exist in space and time, and you know, reactive transport models are designed for this. So I think we all like this figure. We think it's a really nice figure. And basically it shows all these different processes, but also shows the space and time that these processes occur over. You know, so obviously if we want to model the system, we need to sort of go outside of KBase and start using reactive transport models. So what is one of the challenges? Well, after this workshop, you probably all want to model microbial dynamics. You may also want to have a beverage of your choice, but let's not talk about that. And these you want to model at multiple scales, temporal, spatial, multiple dimensions, multiple locations. And so there may be millions of models that we would like to build and run. And that's of course a bit of a challenge, you know, because you know it's sort of hard to build these models. So how do we do that? And I really actually I made this figure at a previous for a previous presentation, and I really like this slide. On one hand, we have like a Illumina sequencer. And on the right hand, we have a monk from the Middle Ages. And there's a mismatch between data generation and model generation capabilities. And any resemblance to an actual modeler is purely coincidental. So, you know, you see a model generation very slowly taking its time. And at the same time, this machine is spitting out data. And that's one of the big challenges over there. And so the question is, why is scaling hard? And thinking about it, we really thought there's really three ways. And first is that like acquiring understanding of what's involved in modeling is complex. I mean, you know, and especially if you're not a modeler by training, but if you're more maybe a microbiologist or a hydrologist, learning reactive transport modeling is actually complex. The second part is getting all the data together is time and labor consuming, especially if the data is heterogeneous, come from different sources over there. And the last part is building and running these microbial models is complex. So what can we do about it? Well, first, make it easy to acquire basic understanding of modeling. And of course, that's what this workshop is about. And second, develop and provide data management, automation, discovery, and access mechanisms. And third is create a microbial modeling pipeline that uses KBase and pFlowtrain so that you can easily create and run models. And that's what to really talk about in the remainder of this seminar. So what I'll do in the remainder of the seminar between me and Becca is we'll talk about an online hands-on tutorial, which should allow everybody to understand key aspects of modeling. We'll briefly go into aspect of data management, discovery, and access mechanism. That's a whole presentation in itself, so I'll just basically allude to some components. And finally, we'll just demonstrate the result of a microbial modeling pipeline that uses KBase and pFlowtrain. Okay, so we, you know, under funding from the Department of Energy and SBR award, we built an online modeling course. And the reason we did that is basically we needed educated collaborators. And why? We worked with a whole number of different people, and we found that time and time again, we were answering questions. Say, you know, collaborators don't need to become modelers, they need to understand the modeling basis. So we created the course, and the key is to make it interactive, hands-on modeling to provide intuitive insight. If you show people equations, it becomes very hard. If you say to people, hey, here's a model, you can change the model and see the output, it becomes easier. So the course was designed to have a low activation energy, so there's no need to install pFlowtrain, intuitive GUI, and hopefully you'll like it. So to get access to this course, you go to this URL here, learn.subsurfaceinsight.com, and I'll leave it up on the screen for a moment. should be a little button that says request access that gives this second window. You type in your email and you confirm that you're not a robot, and then you request access. And then you get a registration link, and with the registration link, you can get a password, and then you can log into the course. So then you go back to the same thing and you use in normal thing with your credentials. We'll send these registration links in probably about like 10 or 15 minutes from now, so you can register right now, and then you'll get these links, and then you can start playing around with this course over there. So this course, and actually there are actually several collaborators, and the list of acknowledgement is not meant to be a graduate course in reactive transport modeling. It's mere comprehensive introduction, which is really designed for people who want to know reactive transport modeling, want to maybe play around with them, but this is not a graduate course. This doesn't replace like going, getting your PhD. We provide an overview of modeling and visualization concepts, chemistry, flow and transport, numerical modeling, and p-Flow-Tran basics. And throughout the course, we have an interactive capability to run p-Flow-Tran models. If you see any bugs or have any course comment suggestions, you can send an email to this address here, or even to me or Rebecca. Okay, so the navigation of the course should be pretty straightforward over there. Basically, and I'll show it here in a moment, you go in the course and you can navigate your sections, subsections, and whatnot. Okay, so what is the key piece of the course? And I don't want to spend too much time on it, but it's basically p-Flow-Tran. You've got the introduction this morning, so I won't belabor what p-Flow-Tran is and what it does over there, but it's a really, really great course. It can do all this really cool stuff. Here's a list of the capabilities over there, and it's great. p-Flow-Tran, it's sort of like everybody should buy one. Okay, and actually it's free, so everybody gets it for free. Now, what is the problem with p-Flow-Tran, as you may have noticed this morning? It's getting it to run and getting it to do what you want when you're haven't been sort of included in the clan and don't know the secret handshake. It's sort of challenging, and that's some of the things we try to deal with. So what we did, and this again was developed under an SBIR proposal effort, is we basically exposed p-Flow-Tran model to a browser interface. So the architecture is the following. We basically have a visual interface, which I'll show you in a moment over there, and you get to play with yourself. And that visual interface talks to a server. The server stores models in a relational database. We use automatic in-file generation using p-Flow-Tran and open source code developed by Satish Kara. And then those models get sent to a HPC resource, which has a standard p-Flow-Tran install. On the HPC resource, we have a p-Flow-Tran scheduler, which is a very simple like Python code, which basically listens for requests and then executes these models and sends the results back. And then to the front end, you can visualize the results over there. Okay, and so the architecture is really nice because, first of all, it allows to expose model parameters. We can say, hey, as you may have seen, a p-Flow-Tran model may have like tens or hundreds of parameters. We can say, okay, this is the parameter that people want to like change with. We can expose that, and people can change it over there. The other thing is it allows to do programmatic model building and modification, and I'll show that in a moment here. So we're very happy with this interface. Okay, so a little bit of housekeeping. Once you get an account, and I'll show you where these buttons are, turn off auto run and sweep models. Comments, and it right now the interface in the backend we use the currently stable p-Flow-Tran version, which is version 2. Glenn Hammond and his colleagues are busy to upgrade to version 3. Once it is stable and released, we'll upgrade to version 3. So right now, if you install version 3 and you download the in files from our interface, you'll have to modify them. If you register, we won't bug you, but we may send you an email once in a while about course updates and the like. Okay. With that being said, let's take a look at the course there. So here, okay. So right now I'm actually logged into the course here. Can everyone see my screen here? So this is the course interface there. And so one of the first thing I want to show here is some of the details about how you look at the model output. Okay, and so one of the things to realize is we can model in different dimensions, 0, 1, 2, or 3D, and we can also model in time or instantaneous, basically like a beaker reaction. And so you can have a model anyway from 0D, 0T to 3D, 1T. And different models provide different understanding. Now, if we look at the output results, and this is sort of like and that may have been covered to some extent this morning, is we can either, and we'll here have a very simple model, a 1D, 1T model, where we have basically 10 blocks, and we basically look at these blocks at different time step, 1, 0 minute, 1, up to 5 minutes. And we can either look at a specific location over time, or we can at a specific time over all the locations over there. Okay, and in pfloatran, the tech file is typically this file over here, and the H5 is that file over there. And pfloat can generate these both files there. Now, if you look at this interface here, there's basically a discussion about how these different models relate and how you can visualize these results over here. Okay, so and again, like, you know, you can sort of hear some introductions, fundamentals, like whatever, models, space and time, and so on. Okay, so now let's take at the model, and this is really the simplest model one can use over there. Okay, and it is a it's essentially like a 0D 0T aqueous complexation model over there. Okay, so so what we have over here, it's a very simple model. Essentially, you know, we basically have like CO2, fully mixed CO2, and we have like a variety of different reactions going on over there, and we can calculate what happens. Okay, and so when we what happens is now when we press this button, I'm running a model. I'm basically sending a model to the server runs the model and brings the result back. Now this is a very boring model because basically it only gives me one data point back, 0D 0T. What I can do here, I say, hey, let me change the modality and use a range of the modality here. And you see, we'll see on the interfaces that the ability to do that is actually pretty much on all these models over here. And so what happens right now is it says, hey, I have a different range over there, and I have for all these modalities, I have basically like a pH that I get for a thing, and you see, you know, what you expect to see over there. You know, so basically you see that you know, your increased modality, you decrease the pH in the model, which is what you expect. Okay, so now what I was doing, I was running this model in real time over here, and you can play around with it once you get an account on the system. Okay, let's see, how am I doing time there? Okay, pretty good. Okay, so now the second model here, so this is sort of a boring model. The second model is a little more complex model. Okay, so again here, click on this model here, and now we have a model which basically is the transport to a through a column over here. So let's see. Okay, so here what we have here is essentially a very simple model. We basically have a column where we have a concentration at the beginning, concentration at the end, and we run a conservative tracer through the column over there. Okay, and I'll just start right now with running a range of models over there, and like running running these models over there. So right now, number of jobs are being generated, getting sent over there, and these is the fluxes to these models over there. Okay, is this what we expect to see? Basically, as we increase the flux velocity, which is shown here on the right-hand side, these decrease the concentration quicker from the initial value over there. So this is what you expect to see. Now you can also go back to this model and say, okay, let me show the menu here, and say, okay, rather than looking in tech, let me look at in the H5 over there, and basically look at in X, and look here, basically, and what you see here is sort of what you expect is essentially the concentration, of course, for all the models is the same at the beginning over there, which is sort of boring. But then if you look later in time, you see different behavior over there. Okay, now one of the nice thing about it is that you can go to this model over here and say, well, here's actually all these models which have been generated. So here is the actual in file, the model file that you can download and play around with in your interface. You can also look at the H5 file and even the output file over there, which is not that exciting over there. Okay, and so so we got a whole number of different models over there, and if you look at the course, you have models of increasing complexity. You know, basically you have models that acid mine drainage and infiltration, you know, adversion things there. And so what the nice thing about it is you can go to these models over there and you can interact with them. So you can change these parameters, you can put your value in there. So here, you know, you say, hey, I want to change this, make my value, move it back and forth over there, and you can play around with these models. And the nice thing about it is because the course is set up so that we have like this incremental change in these models there, you can actually like say, hey, does it actually make sense what I do? And the nice thing about it is also going back and forth between different visualization capabilities and saying, hey, let me look in space, let me look in time, and really make sure that they get it, and say, hey, what happens if I get something over there? Okay. Okay, as I mentioned, you can download this interface file. We're not really sure how many people are going to be hitting the server, and there's some models which are actually quite complex. There's some models from Peter Lickner, which is like 3D models over there. So if things are getting really slow, we'll add some more resources over there. But just to let you know. Okay, we'll switch over. So now we can do these models over there. And well, what's one of the problems is in building these models, you need more than just microbiological data. You need contextual data. And actually, I have to thank James Stegan for that comment over there. And what is the contextual data? Well, depending whether in the water or in the soil, is soil temperature, elevation, soil moisture, soil radiation, vegetation cover, river stage and flow, remote sensing data, snow thickness. And here on the right-hand side, it shows some data. This is actually data from Sentinel, which at the Connecticut River, we're doing some work over there, where you can different bands and you can look what happens. This is data from a snowtail station in Colorado. This is some data from our own temperature sensors. Actually, it's interesting. So we have temperature at depth here in the soil, and actually this is the part of the temperature probe sticking out of the ground. So you see this high temporal variation over there. A lot of this data can be discovered through APIs. But in order to work with that, you need native normalization and integration in a robust architecture. And a large part of what we're doing is focused on that. And that's actually one of the things which I think is, whoever is looking at this is, make sure you can deal with large amount of data, and heterogeneous data is a really important thing. And so that's something which is near and dear to my heart. I won't spend too much time on it. I'll gladly answer any questions. So maybe you thought, hey, they got this cloud-based bFlow-Tran and they got web-based KBase. Can we glue them together to create a microbial modeling pipeline? And yes, we can. Okay, so what I'm going to do now is I'm going to stop sharing my screen. I'm going to hand it over to Rebecca, who will take it from here. So I'll stop sharing my screen. Rebecca, you ready to take over?
Yep.
Okay.
Okay. Everyone should be able to see now.
Yeah, I can see.
Okay. So this is actually a case study that we presented a little bit ago. So it's familiar to some of you, but certainly not to the whole audience. And it's both relevant and we think a really cool example. So I'm just going to go through this very quickly. We looked at river sediment samples from the Hanford site corrected by Emily Graham et al., which included I lost a slide, sorry. Which included a bunch of metagenomics as well as metabolomics and metaproteomics from the Wrighton lab. And they worked with us to interpret this data and get our models curated. So the first step in our pipeline is to define our system. And for comparison, we also used a sort of literature-based model of what you'd see in a standard textbook, very generic microbes compared to, you can see the site-specific model has very specific genomes, which we used in KBase to build models. The chemistry similarly is extremely simple on that classical textbook style model, and again, very complicated in the realistic one based on the Wrighton group's analysis. So even though those classical compounds are generally a good read and they're used a lot in design of wastewater, for example, they found that a lot of these other compounds are very much present and very much important to the microbial metabolism. And so we wanted to see if we could develop a model that would incorporate this information, especially all these really more complicated carbon sources, since most environmental systems aren't necessarily going to be dosed with acetate or anything. So in KBase, not going to spend a lot of time on this because you guys have already spent quite a few hands-on tutorials on this. But as you guys have seen, we developed media based on the environmental concentrations of those key compounds. We used the genomes to build our metabolic models. For the ammonia oxidation, we did manual curation. Some of, well, you've met Kayla and Peng Fei, I believe, helped us fine-tune those and curate to get the actual precise metabolic reactions that should be in there. But then we also did some media-based curation where we would set reasonable flux limits for the reactions we know to be occurring. And both of those worked reasonably well. So then from the flux balance analysis, we used those exchange fluxes as a sort of pseudo reaction to capture what you would see from outside the microbe. Because from the environmental perspective, what we wanted to be able to put into pFlowtran was the outside, the microbe reactions going on. So you guys saw earlier in some of the tutorials, this is the raw, on the left, the raw output from KBase for the exchange fluxes. And we've got a script that uses the KBase API to download the models in FBA and translate it into reactions like here on the right that can then be plugged directly into a pFlowtran in file. And using that, the infrastructure behind the web interface that Roelof was showing you earlier, these can actually be replaced programmatically so that we can swap out these reactions as we change our system. There is still some automation to be done, but we're pretty excited about where it is already. So then, given that chemistry and the microbiology, we then take any physical data we have, which can include that remote sensing data or other in situ collected data, to build the physical side of the pFlowtran model. And then by running that through, we can get the chemistry. Oops, and I'm gonna skip ahead to get this, because it's much more interesting to just show you these models. And these are publicly available. You don't need a login to play with these. But you can say, if we want to just run the baseline model, and then say I want to see what happens with pH, or I can plot the various nitrogen species. It's all very interactive, which is exciting. But then as Roelof showed, we can show ranges. And for this model, we decided to expose initial ammonium concentration, bicarbonate, and acetate concentrations just to see what that would do. So if I say vary the ammonium concentration, sorry. So now we obviously get a lot more in the output, but that was a pretty quick change to show all of those different initial settings. We can also, because as you saw earlier, there are a whole lot of different settings, we can choose different parameters to expose. So in this case, perhaps we want to see what happens if our ammonium oxidizers are running at different rates. So it just depends on what's useful to us and our scientists or our users, what they want to see. But it can be a really valuable tool for evaluating quickly the change that the different things will have. So then the next big step that was sort of addressed some earlier is that obviously running one 0T model or 0D model rather, that runs to exhaustion is still interesting and pretty exciting that we can do it. But ideally, you want to be able to develop an iterative approach. So for that, I've been working on that since AGU when the rest of this was presented. I'm going to switch over here. And here, in addition to the script that will automatically pull down the models in FBA and translate them into the scripts, there is still some manual intervention there to create my new in files. But then another script will spit out a media composition that can be directly loaded to here, and I can run an FBA using the same original model on this new media condition, and basically slowly work towards a steady state. As I run out of any given carbon source, I can see what, given this new media condition, what the bugs are going to do, which still needs some fine tuning, but you can see it instead of just running to the ground when we run out of the first one, let's see, glutamate, it's able to continue and keep cranking on choline. So that was pretty exciting. And we're approaching the point where they're starting to actually generate compounds previously exhausted. So I still need to fine tune the switching a little bit, but by adding successive reactions that will begin to take place as things are exhausted, we can create a continuous system, which is cool. So just a summary. The online course that Roelof showed will hopefully give you a little more background on the reactive transfer modeling stuff, which is a whole lot, and 1 week crash course is really, really quick to try to pick it all up. We also hope you can play with our modeling interface and get a lot out of that. And be able to make use of these tools without necessarily having to become an expert in pFlowTran. And just this pipeline that we're very excited about and that we're continuously developing and improving. And I think that is my last slide.
Okay, so I think we have some time left over. So I'm not sure if there's any questions, but we'll be gladly answering them. I know that we sent out credentials to everybody who had requested them. If you still want other accounts, you can just go to the same page and request them. So this course is open to everybody. So the thing. So Rebecca, there's a question if you can share the link for the KBase narrative that you developed.
The iterative the chemistry-based iteration one?
Mm-hmm.
I can. It's not very well commented right now, so it might be good if I do that first. Because there's not much going on in that narrative. It's really just some models that I built in a different narrative, and then I import media and run them successively. So it's not necessarily the most useful narrative to share.
Yeah, and we're also still, like, obviously writing up some of these results over there on this work here. But yeah, once we'll be glad to share them once we're probably like a little bit further and have them a little bit more documented. Yeah. Any other questions? I'm looking at Discord right now, or I'm not sure if somebody's going to speak up, or Tim, if you moderate that.
Since we have time, I can also show some more of what was going on there. I was rushing.
Okay.
Yeah, no, I think that might be great. I'm not seeing a lot of questions in the chat. I think you addressed the one on Discord. I know that I have not received my email back.
Okay.
From Subsurface Insights, so I don't know if other folks are having issues receiving their credentials.
I think it's been said.
I don't know if maybe I might have signed up before Roelof. Is it possible that there's a conflict if I signed up previously?
Let me check over there. I'm not sure.
Want to check your spam folders, because since a lot of emails went out, sometimes those can get pushed to spam.
Yeah. So
good thought.
Okay, so Chris Miley got in, and I think some people maybe it's PNL, maybe it's the PNL spam folder, like keeping yours out, Tim, there. So I think Swamini was asking what the capacity of the HPC is. So right now we're actually running this on on one of our big iron clusters that we have, which is, compared to the PNL clusters, not very big. It's an 80 core system with 600 gigs there. I mean, I would say the big issue is a lot of these models we showed are essentially like 0D models, and they run really, really quickly. I mean, really most of the time is spent in sending the models to the server and the server sending it back. It's really the 3D models which take a lot of time, but basically all the models that we run here, they run in fractions of seconds. And if you haven't gotten your email, just drop me I think some people have gotten in there. So if you haven't gotten the email, you can also email me or just email learn@subsurfaceinsight.com, and we'll get you in there. Rebecca, you want to share your screen again and maybe go back to some of these narratives there?
Yes. I was just going to answer some questions in Discord, but I'll let you take over and I will share again.
Okay. You're probably better qualified than I to answer these questions over there. Okay, so I guess one person assessed the uncertainty of the simulation over there. I'm not I'm not completely sure what you mean by the uncertainty of the simulation. I mean, like so the answer is we can do like a whole of analysis like on the Jacobian, if that's what you mean. Do you know what would be meant by that? Is that what you mean, Luciana? Let me see.
I think one way definitely Roelof is, you can easily do parameter sweeps, right? So
Yeah.
if you have uncertainty in your input parameters, you can do a whole suite of simulations quickly and see the range of outputs.
Yeah, and one of the things also I want to mention here is right now we expose this through a web interface, but we also expose it to an API, and then actually the API runs quicker. Basically, the web interface talks to an API, and so the API you can basically submit like tens of thousands of models. I mean, we've run. You can actually, and of course, the moment you have like say 3 or 4 parameters, I mean, what you'll notice in the web interface, we limit ourselves that you can only do one sweep, what we call it. You can do only one sweep parameters, because if you have say 4 parameters you can sweep, it becomes very big very quickly. But we've run successfully like thousands of models or tens of thousands of models, and you can then really explore the parameter space very very rapidly. Yeah, and the nice thing about it architecture is that's all there, and that's all it's API-able. So
I guess, was there anything in particular anyone wants to see more of here, either in the narrative or in these 2 online models that I have?
yeah.
Just before I start winging it.
Yeah.
Okay. Like I said, this one, the nitrogen cycling 0D, is the one based on the literature model, which has the very basic, what you'd find in like Metcalfe wastewater treatment manual, which is, as I said, effective, but it is used for treatment. And that's sort of why we chose these parameters to be variable. For example, in this case, we want to see what happens depending on the carbon source availability to denitrification. So as expected, not going to see much of a change for the nitrification side of things. But then it starts to spread out a bit. And we can even extend this range a bit more.
So I think one of the things which is interesting, that in the space of this presentation, we've run probably like 40, 50 different models already. Without you having to write your in file without the thing, and you can visualize the results over there. So it's an extremely one of the reasons we developed this interface is making it easy for people who are interested in running models, rather than forcing everybody to build their own model. And we hope that people find this useful.
So Roelof, this morning someone asked about if there was a GUI for pFlowtran, and so in a sense you've provided at least a limited GUI, right? So how do you choose sort of what aspects of pFlowtran you're choosing to expose here versus what you're setting or fixing behind the scenes?
We can completely control. Basically, we can expose, so we can expose any parameter in the pFlowtran model. So any parameter in the pFlowtran model we can expose programmatically. I mean, obviously there's some things that don't make a lot of sense there, I can't really think of something, but we can expose material properties. So the interesting part of the architecture is this interface is sort of like designed to expose some of the things that people think interesting. But I think what Rebecca showed is that we can have the same model but we expose 3 different things for these different models over there. So maybe somebody's interested in the nitrogen, somebody else interested in the carbon, and we say, oh, we're just going to expose this thing. But we can expose any parameter. The reason why we don't expose all the model parameters, now the interface will be extremely busy over there. But yeah, we can expose every parameter, and basically in the backend we tell the interface for this interface what are you going to show to the user, and what is called, and what are the ranges over there. So yeah, so this is it's essentially like I would claim that this is a full-fledged interface to pfloatnet. We have a 3D and 2D visualization part that we didn't show in there, that we didn't include in this course here, because again, the 3D models take a lot of time to run over there, so we're still trying to work out how to do that, but we do have that component as well.
And what is your sort of policy for access to the system? Students are asking on Discord, can they have access after the summer school is over, or how do you provide access to users, and what are the criteria?
Okay, so this course is free and open to everybody. So so people, the only thing you have to do is they have to register for an account, and then once you have a registered account, you can use it as much as you want. I would say the constraint is if somebody is bringing our service to the niche, we may call them up, say, okay, can you slow it down a little bit? But as I said, a lot of the models we expose here are 0D or 1D. Don't take much time. We have multiple servers we can use on. So our objective is to provide this course for free for the foreseeable future for everybody who wants.
And what is then your long-term vision, or maybe, I guess the right word is business model, for moving this forward and broadening it out for broader community use beyond just the learning modules?
So that's a good question. I mean, like the reality is, like, for the people on the call, so Subsurface Insight is a small business. We're a commercial business. We're not academia. We're not national lab. What our really model is, we build tools for subsurface monitoring, and this for us is a learning tool that we provide freely. We have integration with field data, and that's really the longer term. It's like these models, as you see here, people. So for instance, we're working with some other people who say, hey, I have a site where I want to be able to upload my own composition or other things. It's more a 2D or 3D model that we run there. But this is really meant as a service to the community, also partly because this was funded by the US federal government, and we think it's very useful for people to be able to do this here, to have a low activation energy to these models over there. In the longer term, we have other ways in which we plan to make models. So we don't plan to make money from this course. We don't plan to charge a fee. We don't plan to, but if somebody says, hey, I want to run a 3D model in the cloud that pulls data in automatically from something else, okay, that is more where we work on. So this is maybe to some extent it's a test. It tests our servers, it tests our architecture, and the same architecture is being used for model data integration. And I think that's really maybe the answer to you, is like a large part of the contextual data integration. That is where I think we can provide a service to people and that we do it through a variety of mechanisms, like collaborative agreements, directly funded work, subcontracts, service models. Does that answer your question?
Yes, thanks, Roelof.
Okay, but I saw a question over there of the format of the output files. One of the things which is happening right now, and I just wanted to make sure, like pfloatran is just in the middle of being updated from version 2 to version 3. The version we run in the background and the in files here are version 2. We're probably going to move over to version 3 like in the next month, and we'll take the system down, and then version 3 will run over there. There's a discussion going on right now on the pfloatran mailing list led by Glenn Hammond and other people over there to better define the data format. So there will be an update on the data formats once you migrate to version 3, which hopefully by the mid or end of August or something like that. Okay, so I think it answered most of the questions I see on Discord. Any other questions that you saw, Rebecca, or any other things that people would like me to address here? I guess one of the things I want to mention is and I mentioned very in passing, is PyFlowtran. So PyFlowtran is a code which was developed by Satish Kara out of Lenel, and as part of the SBR, actually, we provided funding to Satish to expand PyFlowtran so it could deal with a whole large number of PyFlowtran parameters over there. And so actually that the PyFlowtran is open source code, so people can grab that as well, and we use it extensively in our backend.
There's actually, since we have time, I wanted to give a quick call out. It was touched on a bit earlier, but we've also been using Reaction Sandbox with some of this.
Oh yeah, that's a good point. Yeah.
I wanted to point out we've been using that to do, as they noted, more advanced kinetics, some of the environmental inhibition, like temperature inhibition, which you can't necessarily get just from the stoichiometry here. My coworker, Ali Mayal, who I believe is in attendance here, is really fantastic with Sandbox and has been putting together some really cool models. Also, we've been looking at death kinetics and decay, which I guess sounds morbid, but is also really, really important, especially in these environmental systems. And we're pretty excited about integrating that into this whole stack as well.
Yeah. Yeah, think. Yeah. The PyFlowtran Sandbox, for people who don't know it, and the PyFlowtran Sandbox is a bit of a acquired taste because it's not that easy to do, but it gives you this incredibly powerful tool you can sort of like extend the PyFlowtran capabilities with, and also couple things that another parameter, and we haven't talked too much about it here, is really the use of parameter estimation. So that's work which is done a lot by Hein Zhu in our team here, and I think that the whole notion of using parameter estimation to get at some of these model parameters is something we hope to touch on in the coming months as well, and we may actually even expose some of those parameter estimation capabilities to the same course over there. So anybody has any questions, you can email learn.subsurfaceinsight.com or Rebecca or me. I think our credentials are here, and we hope that this is useful to people. I think we've had, let me check, so far, we've had 41 people signing up. We have, and one of the nice things of our architecture is that it allows us to distribute jobs across our backend servers over there. So there's this automatic job allocation thing, which goes in machines which actually sit in different places. Right now we're a virtual company, and some of these machines are in my basement, and some of these machines are of the basement in my coworker in Idaho. And they right now, all these basements are being heated by the jobs you guys all submit. So any other questions? I know that probably Michelle is coming up here shortly, Tim, but I think we have a few more minutes, so we'll gladly answer any more questions if there are.
I see some coming up in Zoom.
Did you address this one, Roelof? How much modeling, how realistic is it to simulate, to do modeling with PyFlowtran on a local machine versus using large servers like you guys are making available, or even larger clusters like at EMSL?
So I would say, like, these models that Rebecca uses, these 0D models, you can run on a Raspberry Pi. I mean, you can install PyFlowtran on a Raspberry Pi. And by the way, if you don't know, Raspberry Pi is a $35 like single board computer. So you can install it on there. It will be like a little bit, you have to get like a 16 gigabit like SD card. You have to install it there, and you can run the 0D model on there. So I think for 0D models, you can do that. I think the problem is a little bit like, that figure from Carl Stiefel in the beginning is you want to integrate your modeling into a 3D reactive transport model, and that's, I think, where the crux is. I think all these 0D models, you can run on very small machines. The problem becomes once you start integrating, like for instance, temperature behavior. I mean, say like, I showed some of this data where you have maybe like a temperature profile. You have maybe like an area where you have say like a 10 by 10 square meter area, maybe like a meter deep, and you have like diurnal temperature behavior that you want to model. Things become relatively complex, and I think that then links the fact that you need to integrate your 0D model into your 3D like transport over there, and that's where things start. That's why you need bigger computers. But all these 0D and 1D models, you can run them on, probably the smallest computer you have without any problem. At least from our experience. I mean, I guess the only big challenge is that, installing, we only run on Linux boxes. Getting pflowtrain to run on a Windows box is possible, but sort of painful. On a Mac is pretty trivial. But I guess like once you get it running, these models should not be any computational challenge for the 0D or 1D. Okay, I think people are have been logged in. I think any more questions? Let's see here. So right now, I think 45 people have logged in. We sent about 50 invites, so I guess other people will be coming. Can try it. I mean, like, and we'll leave this open, Tim. So feel free to post this in Discord and invite other people. And I'll just keep you posted. If we need to borrow EMSL. I heard Tim offering EMSL or not. Did somebody hear that also? That Tim said you can have EMSL resource if you want to. So.
Well, you can if you write a proposal.
Yeah.
So one of the nice thing, Nancy, and I just wanted to point it out there, is that the interesting part is we just run a standard pflowtrain instance that we have a little piece of code for. So if somebody says, hey, I want to run a really big model, we can put a pflowtrain engine on the EMSL computer, and because it's designed to sit behind the firewall, the only thing it would basically retrieve jobs. It would talk to the server, say, hey, give me a job, and then run it and send it back. And so the nice thing of this architecture is you can actually have, you can actually have people have just install pflowtrain and then get the little Python code we have, which just basically talks to their server, say, hey, give me a job. And it's an extremely scalable distributed architecture. So I may write a proposal, but I think so far we're good.
Well, please do. We will have a call for proposals coming out, like either this week or next week, for these what we call exploratory. They're one-year proposals, and access to our computational resources is definitely included with that.
Yeah.
But there are many other capabilities that at EMSL that you can link that with. So I am only joking in jest when I say send in a proposal. This is an actual opportunity.
Yeah. Yes, and I think one of the things there, and I want to sort of actually circle back to some of the challenges there is the integration with the data, like that was shown on the first day with Wonders, is something that we're really working on very hard, because that's, I think, a large part of how do you pull this data in, how do you bring that data together, how do you build those pipelines, because the interesting part, of course, we have this data tsunami, and so what you really would like is saying, hey, data get analyzed at JGI or EMSL, boom, now you have the model, and so that nobody really has to do this. And I know to put these models out to work, but they'll find something else. But basically that, and that's the vision we have. And I think if you can do that, it will allow enormous amount of stuff. And I think we built infrastructure, and I think that other people can build other infrastructure which is similar. But I think it shows that you can actually automate a large part of this effort very easily. So.
That's wonderful. Yeah, it's a very exciting opportunity, and I think you're absolutely right. It's that pinch point that really translates the data into knowledge, and then, as Tim was pointing out, that whole MODEX cycle where the model then drives the next round of experiments. So, yeah, just getting that crank and the gears working we're right there. So yeah. It's very exciting.
Okay.
Okay. Well, we have.
Okay. Sorry.
Oh, I was just going to say we have about 4 minutes before we're due to transition to Michelle, but if there are any more questions, I know personally I'm still having difficulty logging in. It says I'm not a member of the team. I feel rejected, but I'll follow up with you later, Roelof, to log in. But
yeah, anybody got problems, just email me directly or email, and it's possible that we miss your thing there, but we'll if you cannot get it signed up to the thing, just email me directly and we'll get it squared away.